All right, so for section 13, this section is titled Central Limit Theorem and Confidence Intervals, which I think is actually a very interesting choice of title, given that, I don't know, you'll see. But for this section, I will say this section has more important things, proportion-wise, more important things. The central limit theorem is one of the things that I've been asked the most in job interviews in like different ways. People ask me straight up, like, what is the central limit theorem? I've been asked, what are the implications of the central limit theorem, or like, why is it useful for us as data scientists to use the central limit theorem? And so on a slide later, I'll just straight up have the answers to that. Introduction to sampling and sampling statistics, the labs before and after the central limit theorem sort of set up what's coming in T distributions. And then there's confidence intervals, which is kind of like a separate but overlapping thing. So that goes to say pretty much every lab in section 13 is important. But I think that with confidence intervals, I will actually in the slides go over confidence intervals before talking about the T distribution, if that makes sense. So that's kind of the structure of this section, a little bit here and there, but we'll make it through. Any questions so far? Cool. All right, so to get started, let's start as usual with an overview. We're gonna start off with our first statistical test because we ended off section 12 introducing z-scores. If anyone remembers the end of Tuesday, we started talking about z-scores, and then we're actually gonna do a quick example of a one sample t-test, a z-test, sorry. And then we're gonna talk about central limit theorem. As I mentioned, very important concept to understand. Little bit about sampling. The part of sampling that I'm gonna emphasize more is the idea of a standard error and how that is different from a standard deviation. Confidence intervals, as I mentioned before, confidence intervals can be in the context of, in this section, they do it in the context of a T distribution, but I'm also going to talk about it in the context of a normal distribution. And then finally, I'll introduce a T distribution. Yeah, and then the next section we'll be talking about t-tests. But we'll sort of set that up here for now. Cool. So we're going to start with our first statistical test. This is a test that this scenario comes from Learn. So that's just like, we're going to read through this and we're going to solve, or we're going to conduct a statistical test based on this. So data scientist wants to examine if there's an effect on IQ scores when using tutors. So to analyze this, she conducts IQ tests on a sample of 40 students and wants to compare her students' IQ to the general population's IQ. The way an IQ score is structured, we know that a standardized IQ test has a mean of 100 and a standard deviation of 16. And so when she tests her group of students, however, she gets an average IQ of 103. So based on this finding, does tutoring have an effect? So this is usually when you would want to conduct a statistical test. You want to see if, like, all right, we're doing an action here. We want to see if there is a statistically significant impact of the action. So yes, the average IQ, yes, it went up, but is it a significant enough increase to say that tutoring actually made an impact? Or is it like maybe by chance that the 40 students that she picked happen to have just a little higher IQ? That's kind of the basis of this test. More commonly, other common tests that we might do, we're going to talk about A/B testing later on. So in the context of marketing, for example, A/B testing we'll talk about, I believe, in section 16, but quick example for now. Let's say you have two different marketing campaigns and you want to see which one does better. You would compare the performance of one of them, performance of the other. Maybe you want to look at how many clicks, how long the page views are, how much revenue each one brings in. And you would conduct a statistical test to see if they are significantly different. So there's this whole idea of statistically significant difference versus just like a regular difference. Because straight up here, we're looking at, all right, 103 versus 100. 103 is higher, the tutoring works. But here we're actually using some ideas of statistics because there is a chance that by random selecting these 40 students, they happen to have a higher IQ. So we want to make sure that it's statistically significant. Got it? It's kind of like a hard, at least for me when I was learning this, it took me a while to grasp that, like, yes, 103 is higher than 100, but is 103 significantly higher than 100? And so that's what we're trying to get at here. Any questions before we move on? Because I think it's important to understand the setup of this experiment. All right, so I kind of broke down the testing process into 6 steps. Slightly different from the labs, but it's kind of the same. So first you want to set up your hypotheses. And in this specific example, the hypotheses, I'll actually talk about it later, right after this slide. We want to see if tutoring has an effect. So after you set up your hypotheses of tutoring has an effect or has no effect, you want to pick the statistical test based on your experiment. So this is where that hopefully all the different parts of this mod come together, because throughout the mod, we're going to be talking about many different statistical tests. The first one is this one sample Z test, but as I go through statistical tests, I'm going to lay out what are the conditions that you want to have for each test, because I think one of the hardest parts of statistics is deciding which test to conduct. And so hopefully I'll make this clear. The third step is to pick your alpha, your level of significance. I'll explain a little bit of what that means later. You're going to calculate your test statistic, find your p-value, and then interpret. And I'm going to walk through all of these steps for this very experiment to see if tutoring has an effect on students' IQ. All right, so setting up your hypotheses. Every statistical experiment starts with a null and an alternative hypothesis. So typically the null hypothesis represents no effect. So here you can see at the bottom left, the null hypothesis, which is usually denoted with like a H sub 0, so H with a subscript of 0, and no effect. And in this case, no effect is saying that your sample mean, so because remember, she took a sample of 40 students, the sample mean is statistically equal to mu being the population's average. So actually, let me backtrack a little bit, or let's backtrack to the middle here and talk about what data we have. So this is the data that we have. The population has these parameters. So the population has a mean of 100 and a standard deviation of 16. So that means on average, the IQs are 100 and they vary by an average of 16 IQ points. And the sample, which is usually denoted by X bar, it's usually X with a bar on top of it, but I couldn't figure it out in these slides. But it's usually X with a bar on top of it. And the sample statistics are that X bar is 103, that sample average is 103, and there were 40 students in that sample. That's also important. So null hypothesis represents that there is no effect. So in a null hypothesis, statistically, the X bar is equal to your mu. There's no difference between the population and the sample. Now to set up the alternative hypothesis, we have to consider a couple things. First, question?
Yeah, quick question, Yish. So just to be clear, so for the standard deviation of 16, is that always 1 unit?
What do you mean by 1 unit?
Well, basically, if it goes from 100, if I say, okay, the standard deviation is 16, well, then that goes to, what is that, 84?
Yeah, so
that it?
So kind of. So the standard deviation means that on average, the deviation of each point from the mean is about 16.
So then, okay, that's fine. But then what I mean is if I say, oh, so the sample there with the X bar is 103, right? So then if I say, well, the standard deviation for that is 16, is it going to be like, okay, 119? Do you get what I mean? Or
Okay, I see. All right. So the standard deviation is calculated per group.
okay,
So this standard deviation of 16 is just for the population.
gotcha,
The sample actually has its own standard deviation that we just don't happen to have here. So
gotcha. Okay,
if we had like all 40 values of the IQ, we can actually calculate their own standard deviation.
so the standard deviation doesn't tell me about like each individual like point or plot or every,
Exactly.
it just tells you the standard deviation itself. Okay, gotcha.
Yep, that's right. That's right. Standard deviation describes a group, not one single point.
Gotcha. Okay, thank you.
Yep, you're welcome. That's a good clarifying question. All right, so back to alternative hypothesis. So when we're constructing an alternative hypothesis, there are a couple questions that we want to ask. So first, is the test one-tailed or two-tailed? So one-tailed or two-tailed basically means, are you looking for if something has increased or decreased? That is a one-tailed test. If something has increased, if we're looking at like, so in this case, it's a one-tailed test because we only care about if IQ has increased. So that means we only care about it moving in one direction. There could be other experiments that we're looking at it at like if a number decreases. So maybe we want to see, I don't know, does underage drinking have an effect on SAT scores or something? And so we want to see like, all right, if SAT scores are lower for this group, then yeah, it's a one-tailed test on the left. So in this case, it would be a right-tailed test. Two-tailed test is if you're looking for if something is different. So if you don't care about whether the number goes up or down, that would be a two-tailed test. And then so in constructing this alternative hypothesis, we can see here, we have X bar being greater than, or actually not greater, it shouldn't be greater than equal to, it should be just strictly greater than. So I'll make that change later, but it should be strictly greater than mu. It shouldn't have that little equal sign. So the alternative hypothesis is that X bar is greater than mu. If it was a left-tailed test, it would just be smaller than. And if it was a two-tailed test, you would just have like the not equal to sign. So that's how you would construct an alternative hypothesis. So for tutoring to have an effect, we actually want to reject the null hypothesis. So when we have hypotheses, you usually reject hypotheses. The opposite of reject is accept, but due to like, I don't know, linguistics in the statistics world, we actually never accept the hypothesis. We only reject hypotheses. So just language-wise, you always say you reject the null hypothesis or you fail to reject the null hypothesis. Well, this is just like a little like, I guess, linguistic language thing. So for tutoring to have an effect, we're going to reject the null hypothesis. And if tutoring doesn't have an effect, we would say we fail to reject the null hypothesis. And how we determine whether we fail to reject or reject the null hypothesis, we'll see in the upcoming slides. All right, so.
Oh, sorry.
Yeah, please.
I know you said it was incorrect, but like, is it possible for the two hypotheses to have overlapping values? Like,
yeah.
Could be, you know.
There aren't. So the two hypotheses should not have overlapping values, which is why this is incorrect. It's either equal to, so the null hypothesis is equal to mu, and the alternate hypothesis is that it's strictly greater than mu. So it never has overlapping values. That's a great clarifying question as well. All right, so these are steps 2 and 3, which is picking the test and also picking your alpha. So first couple points is just saying that our first test is a one sample Z test. So this is the first test that we're being introduced to. It's just called a one sample Z test. And the conditions of doing a one sample Z test is that you know your population's mean and standard deviation. And you know this for a fact. So very often you actually don't know your population mean and standard deviation. There are estimates out there for like the average height of everyone in the world, but we can't actually know. You can take a census and like proxy that, but you can't know the population mean and standard deviation. So this is a very specific condition that you can, these are the conditions that you would use to conduct a one sample z-test. As long as you know your population mean and standard deviation, you would conduct a one sample z-test. So that's picking the test. As we get to more and more tests, I'll list out the conditions for those as well. So here, step 3 is picking alpha. So alpha, which is sometimes denoted by that like Greek letter A, is your cutoff value, which is your threshold for rejecting your null hypothesis. Typically, it's set at 0.05. Another, I guess, what's this definition is if you ever hear the confidence level is just 1 minus alpha. So you would interpret your results as, with a confidence level of 95%, we can reject or fail to reject the null hypothesis that blah, blah, blah. So alpha being your cutoff value at 0.05, if you want a stricter test, so let's say we want to be like absolutely certain that tutoring has an impact, you would actually set a lower alpha. So if you want to like have more leeway for tutoring, then you would set a higher alpha. Does that make sense? All right. I think all of these will sort of come together as we see the test being conducted. All right, so that's picking the test and alpha. So steps 4 and 5, I know that these slides are really wordy. Sorry about that. But yeah, steps 4 and 5 are calculating the test statistic and your p-value. So for a z-test or any z-test, whether it's one sample, there's actually other z-tests that I don't think we touch on we do not touch on the other z-tests in this curriculum, but the most common one is the one sample z-test. The test statistic is a z-score. So every test has an associated test statistic. So for the z-test, our test statistic is the z-score. And this line is just to remind us what data we have. So z is calculated, and I think this was mentioned at the end of last session. To calculate your z-score, we take x bar minus the population mean divided by the population standard deviation divided by the square root of the number of things in your sample size. So in this case, x bar is 103, mu is 100, standard deviation, sigma, is 16, and n was 40. This calculator, type it in Python, comes to 1.19. So that's our test statistic. So after we get our test statistic, what we do is we actually look up the associated probability from the z table, and we remember the z table from last time. So I'm going to open this up again. So we're going to look up this test statistic from the z table. So here's 1.19, and let's move this bar away. All right, so 1.19, how we read this, so you can actually get negative z-scores as well. So that's on the first page. So let's look at 1.19. So it's 1.1, and then we trace it all the way across to 9. So we get 0.883. So that means the associated probability of the z-score 1.19 is 0.883. This actually is a pretty good diagram of what this is showing, is that saying that there is a probability of 0.883, that this shaded area is 0.883 out of the whole thing. Does that kind of help like visualize what's happening? So the z-score here is 1.19, and this is actually our standard normal curve, if we remember what that is. This is a standard normal curve of a mean of 0 and a standard deviation of 1. So our z-score is actually measured across here, across this bottom line. I'll have a couple more diagrams later that might help, but this line is centered at 0, and this is our z. And in our case, this z was 1.19. So it's saying the probability of having something less than z in a standard normal distribution is 0.883. What exactly that means, it'll we'll like sort of build on this and hopefully things tie together a little more. All right, so associate probability is 0.883. So actually what we can, how we can interpret that is that the average IQ of the tutored students, those 40 tutored students, is greater than 88.3% of the population. So for a right-tailed test, this is something that you just have to do that's kind of procedural. The p-value is 1 minus this, this amount, and we'll sort of see why later. We'll see this in the next slide. So the p-value is 1 minus 0.83. So our p-value is 0.12. So we do this minus thing only for right-tailed tests.
Okay.
Yeah.
So, okay, quick question. So, so for the, what is this? This says the average IQ of tutor students is greater than 88% of the population. How do I know that's different from before? What I mean by that, I don't know if that makes sense, but what I mean is without that test, like, how do I know that wasn't the case before? Without doing the Z test.
Yeah, so we actually still don't, well, let's see. Yeah, I think that's kind of what the purpose of the Z test is. Because,
Okay.
you know, we had the number 103 and we had the number 100, but we didn't know, like, in context, is 103 compared to 100, is it much greater, right? Because it also kind of depends, like, so let's think about this. If the, let's say the standard deviation was way higher. So let's say you can have IQ scores, you have a lot of people with IQ scores of like 10, and you have a lot of people with IQ scores of 190. In that context, 103 is not a big difference at all. However, if you had a very small standard deviation, let's say like you have a ton of people, like maybe like most of your values are between like 99 and 101. In that case, if your tutor students are getting 103, that makes a huge difference.
Sure.
So the Z score actually sort of takes that into account.
So now we're kind of getting closer to knowing that whether there's a difference in the tutoring.
Exactly.
Got it. Okay. Gotcha.
Yeah. So this Z score takes into account, the standard deviation of the population to see, like, you know, based on this context, like based on where everybody in the world is on this IQ scale, how does 103 compare? And so you get a Z score of 1.19 that sort of translates to a p-value of 0.12.
So would it be correct to say that doing a Z test helps to normalize the sample?
Absolutely, yes. That's absolutely what it is doing. Yeah, that's exactly what it's doing.
Okay, all right, thank you.
You're welcome. So one thing to note is 0.12 is greater than our alpha of 0.05, because we set our alpha level at 0.05. And so we're gonna put this all together on one image, and hopefully we can explain what goes on here. So, all right, this is a graph of, so this is 1.1, was it 1.1? 1.19. So this line here from red to blue is 1.19. So as you can see, this is the Z statistic. And this is the point where our tutored students lie. Because our alpha was set at 0.05, 0.05 alpha means that we want the area under here to be 0.05. Got it? So the area under this part from the red line onwards is 0.05. The p-value that we got gives us an area of 0.12. So this is our threshold. We mentioned earlier that alpha is our threshold. For something to be significantly different, it actually needs to be past our threshold. So for these tutored students to have like a statistically significantly higher IQ, they should actually have a Z statistic past this alpha value. So based on this, anyone want to make a guess of whether tutoring had an effect or no effect?
It didn't, there's no effect.
Absolutely, yeah. So based on this, because the Z statistic of the sample didn't cross the threshold, there was no effect. So this is kind of like the way that I always pictured this when I'm doing this kind of problem, because just comparing these numbers of 0.12 and 0.05, especially when you're looking at different directions, is not always super clear to me. So I kind of always like to draw it out and have it in this way and sort of like map out where the alpha is. Because I know that this area is 0.12, 0.05 has to be to the right of it. And so therefore I know that this is not statistically significantly different. So tutoring actually didn't have an effect. And therefore we failed to reject the null hypothesis. Cool. Any questions?
One quick question. So let's say if the alpha was changed, will it make the difference in the calculation?
Yeah. Well, in the calculation, no, because we're only compare. So the reason why we set our alpha first, it's sort of like, you know, we set the benchmark before we do our test, because, you know, if we already see this and are like, okay, well, if my alpha was at like 0.15, then tutoring has an effect. So we always have to set our alpha first. And so all the calculations was independent of alpha. All the calculations that we did here didn't have alpha. So yeah. So if we had changed our alpha back in like step 2 or 3, and alpha happened to be like here, then yeah, tutoring would have had an effect. But when you're setting up an experiment, you want to set the conditions and the threshold first, so that, you know, you're like, you sort of set like how strict you want your experiment to be, but also like typically is always 0.05. So tutoring, unfortunately, in this case had no effect.
So any specific parameters are there for setting alpha?
No, not really. It kind of, the standard is 0.05. So alpha is usually set at 0.05. And actually you can actually look back and find where 0.05 is in terms of a Z statistic to compare. This is kind of doing things backwards, but you can sort of see, all right, I want 0.05. So that means the area on this side should be 0.95. So you can actually look back in here and trace back roughly where 0.95 is. So if we trace back, all right, 0.9495, so somewhere around here, 1.64 will sort of be like your alpha's Z-score. So based on that, you already know that your Z-score is not high enough to cross the threshold. So that's kind of like, you kind of can like skip a step by doing that, but typically you want to take a look at the p-values.
Okay.
But yeah, in this case, tutoring had no effect.
Wait, where do we set the alpha again? Can you go back to that slide?
Oh yeah, so we set alpha back after we pick the test. So usually when you're picking the test, along with picking the test, you pick your alpha. But typically alpha is 0.05, unless you want to be stricter or more lenient. So if you like, let's say implementing tutoring is so expensive that it will only make sense if it definitely makes a difference. In that case, you want to be more strict on like whether tutoring has an effect. You would set your alpha to like 0.01. So then it'll be harder to prove that tutoring has an effect. So if it really does have an effect, it'll be, I guess, more worth it. If that makes sense.
Yish, question. Can you go back to the visualization?
Yeah, absolutely.
So we set the alpha at 0.05. And I may have missed it, but how did you decide to plot it there?
Yeah. So alpha being 0.05, it wasn't on this visualization. So I actually just looked back and I looked it up here and I looked where 0.05 would be. And so since this Z table shows you the area here, I just looked up which Z score gives you an area of 0.95. And so 0.95, I traced it back to 1.64. And so this is roughly 1.64.
Gotcha. Okay, cool.
Yeah,
All
it's
right.
definitely not super accurate, but I think it still gets the point across.
So plotting it is basically, so if the alpha is 0.05, you find on the z table the difference of it, and then you just whatever that corresponds to, and then you can plot it. Gotcha.
Yeah, you can do this. You can do it this way, or you can. And I know like some people will like draw out this normal curve and just shade under the graph. If you know that like this blue area is 0.12, you already know that it's more than 0.05. So by the same logic, because this is 0.05, this is 0.12. It's just like a bit of comparing
Sure.
to do. Yeah,
Okay.
so you can compare by the p-values or by the z-score. But mostly people compare by the p-values. But cool. This is our first statistical test. We'll be doing a couple more over the course of the mod. I think we'll be doing one more on Monday and a couple more next week. But yeah, this is the general structure of conducting a statistical test. And we'll see for like different tests, there are slightly different conditions in which you want to conduct the test. So we'll look at those when those come around. But cool, any questions before we move on from testing? Awesome, because this was like kind of the bulk of this study group. Awesome, so central limit theorem. I just have this one slide on central limit theorem, but these are all important words. So officially, the central limit theorem states that independent random variables summed together will converge to a normal distribution as the number of variables increases. So what does that really mean? Independent random variables, and it doesn't matter what their distribution is. So let's say you have a random variable that's like, I don't know, shaped like a rainbow, shaped like a wave, shaped like, I don't know what. Any bunch of random variables, as long as you add them together, you put their distributions together, the idea is they will start to look like a normal distribution as the number of variables increase. So the more random variables you throw in there, it'll start to look like a normal distribution. More for our context, I personally like to use this definition, which is the distribution of sample means of any population as the sample size increases will converge to a normal distribution. So regardless of whatever your population distribution is, as long as you keep pulling samples from this population. So for example, let's use like heights of everyone in the world. And we pull samples of like 50 people at a time. And for every group of 50, we just take note of what the mean height is. So if we plot all these mean heights of all the different samples, let's say we have 1,000 samples of 50, 1,000 samples of 50. If we plot all their means together, it should start to look like a normal distribution. There is actually a lab that walks through like taking the means of populations. And as you can see, as you increase the number of samples, it starts to look more and more like a normal distribution. And the implication of that, which I think is very important, is this allows us to use sample statistics to make inferences or estimates on the population. So basically, we can make conclusions on a population based on what we're seeing in different samples. Because it's going to be like, for example, like the census is going on right now, right? And there's no way to survey every person. But you're going to use census data that I don't remember what's the percentage of people who fill out the census, but let's say like 50%. We're just going to use 50% of the population to make inferences or estimates on the entire population. And that's the idea of like, that's sort of using the idea of the central limit theorem, that like, you know, the mean of the samples will sort of start to look like the mean of the population. Sound good? This is more of a conceptual thing for sure. This is definitely one of the definitions that I like wrote on a piece of paper over and over again so I would remember. But the idea is that you can use sample statistics or like sample statistics, meaning like the sample mean, standard deviation, other things that describe people, to make inferences or estimates on the population. Any questions on this?
Yeah, is there any limit on the, like for example, if let's say 100 is the population, And is there like a statement where it says that, okay, if you have, let's say 30% of the population, right? I mean, these random variables accumulate to 30% of the population, then your right distribution will be getting to normal, or there is no definition or as such.
There's no, yeah, there isn't really like a threshold saying like, all right, only after like a certain number, it will start to look like a normal distribution. The idea is that the more samples you have, or the more variables that you have, it will start to look more and more. So probably when you have like 1 or 2 samples, it will look nothing like a normal distribution. And as you increase that, it will look more and more normal as the number of samples increases. Yeah.
Okay.
Good question. All right. Ready to move on to the next thing? Cool. So there's a couple labs on sampling statistics, but the main thing that will sort of lead into the t-distribution is the idea of a standard error. So standard error, very similar to standard deviation. It basically is sort of, if you look at like the conceptual definition, it means pretty much the same thing. The higher the number, the more spread out your data is. So while standard error uses statistics, standard deviations use parameters. So what that says is that standard deviation technically is only used when you're talking about a population. So anytime you're talking about not a population, so a sample, if you're talking about a subset of a population, you're actually using standard error. In the lab, there's a bit of like explanation of like why that is the case. There's actually also a really good video on that playlist explaining why. So I won't go too much into it, but just know that if you have a sample, standard error is calculated by taking the standard deviation of the sample divided by the square root of the number of items in that sample. So here, this quick little formula. This is this sigma is the population standard deviation. So standard error is this one. This is what standard error is. So sigma is the population standard deviation, which here we're approximating with the sample standard deviation. So because there's no way to know what the population standard deviation is, usually, we're gonna approximate the sample standard deviation. We're gonna approximate that with the sample standard deviation. So let's say your sample is of 40. Let's say it has a standard deviation of 10. We're gonna assume that 10 is also the standard deviation of the population, and then just divide it by the square root of the number of items in your sample. That's just the formula of how it's calculated. I will link to the direct videos that explain this. But that is just a new terminology for what's coming up in the t-distribution.
One quick question.
Yeah.
How do you use the what do you call it, tilde?
Yeah. This part.
Yeah.
Yes.
What
yeah. This is just showing that it's like estimating. So yeah. So we just know that S is estimated by this sigma is estimated by S, which is the sample standard deviation. So really, formally in math, I guess, you would just take sigma of x bar is equal to S divided by square root of n. Because we don't have this population standard deviation. Because in real life, very rarely do we have the population standard deviation. Yeah.
Okay.
All right. So next big thing that we're going to talk about is confidence intervals. A little bit of like a gear shift, but we'll come back to standard error in a little bit. So confidence intervals is another definition question that is asked pretty often in interviews. So a confidence interval is a range of values above and below a point estimate, and point estimate I'll talk about later, that captures true population parameter at some predetermined confidence level. All those words kind of sound like gibberish. I agree. So the more, I guess, friendly definition is that a 90%, what a confidence interval does is that a 95% of confidence intervals constructed in some manner contain the true population mean. And that is a definition that is hard to grasp. I 100% think that, but that is kind of the idea of what a confidence interval is. Later, as we discuss more about confidence intervals, I'll sort of like try and explain what that means. What a confidence interval isn't, it is not the interval that contains 95% of the values. That's a common wrong definition. Or like people usually assume, I don't know, but that's a wrong definition. A confidence interval does not contain the values. Confidence intervals is something that is actually constructed repeatedly, and 95%, if we're talking about 95% of those intervals will contain some population parameter. And when we talk, let's talk about just how we construct it, and hopefully like things will come together. To calculate confidence intervals, you take the mean plus and minus a margin of error. So what this margin of error is depends on your underlying distribution. And so far, the only distribution that we've talked about is the normal distribution. So if you know your population standard deviation, which is in the case of that one sample Z test, your margin of error will be calculated by taking the Z score of your confidence level multiplied by your population standard deviation divided by the number of things in your sample. The curriculum doesn't really go into confidence intervals on a normal distribution, but I think it is something that to be aware of, that you can actually calculate confidence intervals on a normal distribution. The labs talk about confidence intervals on a t distribution, which is what gets a little bit confusing because we're now introducing a new distribution. But yeah. So for example, a context that you would use this is, all right, what are the margins for your confidence? Let's go back to that, let's go back to our earlier question about the IQ scores. What is the confidence interval? What is your 95% confidence interval for that earlier problem? So earlier problem being, let's see, we have the mu of 100, standard deviation of 16, and then we have these statistics. The only thing that we need from here is that n is equal to 40. We will calculate that by taking the mean, which is 100, and then plus and minusing Z multiplied by 16 over square root of 40. In this case, Z, you have to think of it as a two-tailed test. Let me actually pull up an image so I can make it a little bit clearer. So let's take this one. I want to pull this up and make it bigger. All right. So in a two-tailed test, so let's say we want a confidence interval of 95%. It's kind of confusing because 95% means you have 2.5% on each end. Does that make sense? So this middle part is 95%, and then you have 2.5 on either end. And so we actually want to calculate these values. And at a Z of 0.25, or sorry, at a p-value of 0.25, the Z scores are plus and minus 1.96. So for a confidence interval of 95%, the associated margins have a Z score of 1.96. So it's pretty much looking back at the Z table, knowing that we want each of these to have an area of 0.025, looking back and finding out what the Z scores are. Probably never have to calculate this by hand. But the idea is that these are the Z scores, you'll multiply it out, and then you will arrive at your confidence interval of the mean, which is 100 plus minus whatever this arrives at. So you'll have some interval. That make sense? And so what that interval means, you're going to construct a bunch of intervals in this manner for different samples, because you have different samples. And 95% of confidence intervals constructed in this manner will contain the true population mean. So that means 5% of the intervals that you're constructing in this manner will be way off and will not contain the population mean of 100. Cool. Yeah, it's kind of like a hard thing to grasp. Why this is important for our purposes is because when we run some models, there will be some outputs of confidence intervals, and that's how we need to interpret them. So calculating the confidence intervals is less important. We just need to be able to interpret the confidence intervals. All right, so this was like kind of like an important tangent because we're going back to t-distributions. So our next study group is going to be talking about t-tests. And before we get into t-tests, we have to understand a t-distribution. So as I've kind of alluded to when we talk about standard error, we use a t-test when we don't know our population standard deviation. So yeah, when we did a z-test, we knew the population standard deviation. So t-distributions are used when we don't know this sigma, and it introduces a new parameter, degrees of freedom. So the idea of degrees of freedom is the number of items in your sample minus 1, and the higher your degrees of freedom, the more normal it looks. So typically, a t-distribution sort of looks very similar to a normal distribution, but has higher tails. So if we take a look at this first diagram here, the blue one is our normal distribution, and our red one is a t-distribution. So t was formulated by, actually, it's called the student's t. I don't really remember the history of it right now, but it's more for samples. And it has these fatter tails. So the more degrees of freedom that you introduce into your t-distribution, the more like a normal distribution looks like. So this just shows adding more degrees of freedom. So 1, you have 2, the green line is for 2. And then when you have 30 degrees of freedom, it pretty much looks the same as a normal distribution. So I talk about this because you do confidence intervals in a t-distribution. And this is the calculation of it. So, all right, so we're gonna break this down. First, we're gonna see something that's very similar to what we were doing before. We have the mean plus and minus some margin of error. So this is the same thing that we were doing back here with the mean plus and minus some margin of error. The structure is the same. But here we have x bar being your sample mean. So here you don't really know what your population mean is either. But you're using your sample mean plus minus this margin of error. So this margin of error itself has some parts to it. So the part that should look kind of similar is this s over square root of n. So s over square root of n is our standard error. Very similar. Standard of error it looks kind of similar to this when we're doing the margin of error here, where we had the standard deviation divided by root n. I should have put it side by side so I don't have to keep switching. But we have standard error here. And also very similar, here we were taking z multiplied by this part. What we're doing here is we're actually taking a t multiplied by this part. So t is our new test statistic here. T works a little bit differently from z, actually a little friendlier than z. So if we look up the t table, and we actually get our t from the t table is set up in a way that is helpful for us, especially when we're doing confidence intervals. So for t values, t tables, what you would do is you would look up what kind of test you want to do. So do you want to do a one-tailed or two-tailed test? Usually if it's a confidence interval, it would be a two-tailed test. So here we have 0.05 as a two-tailed test. And then you'll look up your degrees of freedom. So rather than doing just by the z-score and looking at the probabilities like that, you just have to look up what your alpha or what your confidence level is, and then look up your degrees of freedom. And so here we know we're in this column because two-tailed test, which is confidence interval, we want 0.05. And our sample size was of size 40. So our degrees of freedom are 40 minus 1, which is 39. And here, there's actually no 39, so we'll just estimate by going to the closest one. So we'll just look at 40. And so our t statistic here will be 2.021. And then after that, it's the same math to figure out the confidence intervals. But the real takeaway here is just how we interpret a confidence interval, because in all of the models that we run, the confidence intervals will be output for us. So calculating it, less important, but it's good to know sort of where it comes from. I know there's like a lot of parts to it, but yeah. Any questions? All right. We will be diving more into this t distribution. I know like the whole confidence interval thing is a little bit abstract now, I'm sure, especially for you guys who it's like your first time seeing this. But the confidence intervals labs, the confidence intervals labs, I think are pretty good. And also in the next section, we will be talking about t-tests a lot more. So don't worry if you don't understand like the whole idea of like that t-distribution just yet, but try and get a sense of what confidence intervals are and how they're constructed and how you interpret them. And yeah, I understand this study group was a lot of stuff. Central limit theorem, very important as well. Central limit theorem is something that like I would like maybe write on a post-it and like stick it somewhere where you always see it, because that's very, very important. But yeah, any overall questions about stuff that we talked about today?
Just a quick question. In this section, which are the labs very important, or all of them?
All of them. All of them. This is a shorter section compared to the rest, but yeah, all of them.
Mm-hmm.
Yeah, pretty much for the next section. Yeah, it's gonna be almost all of them as well, but we'll get to that when we get to that. So all right, just to wrap up, Monday afternoon, we're doing this extra probability session. If you want me to talk about specific questions, because I already have some shortlisted, please let me know so I can talk about them, maybe like replace one of the ones that I was going to talk about anyways. So if you have a specific one that you want me to talk about, please let me know. If not, I will just talk about like a select few, which will be like one example of like using permutations, using combinations, using factorials. I think I'll talk about like one conditional probability one, even though we're actually going to get way more into conditional probability in section 17.
Is it Monday or Tuesday?
It will be, I believe it was Monday, 2 p.m. that came up as the most voted for one. Yeah. So it will be Monday, 2 p.m. Eastern. It will be recorded as well. So if you can't make it, don't worry about that. But yeah, any questions that you want?
I thought it was dated 15th. So I just got carried. I mean, 15th is Tuesday. So that's the reason I just.
Yeah, so it's actually going to be on the 14th.
Okay.
Yeah, that's right. So it'll be on the 14th. I'll send out like a Zoom link when that's ready.
Perfect.
And yeah, any specific questions from section 11 you want to talk about or want me to talk about, please let me know. And I'll also talk about that binomial theory, binomial distribution thing at the start of that, just because I think it's very cool and just good to know that it exists. Cool. Any final questions before we end off?
Perfect.
All right. Well, in that case, have a good night, everybody, and enjoy the weekend. Bye, everybody.